Welcome to UV Physics Academy. So here, this is the next question. Find the eigenvalues and eigenvectors of Pauli matrices. Now first take this x, which is 0, 1, 1, 0. If you want to find eigenvectors, first we have to find the corresponding eigenvalues. So eigenvalues, how to find eigenvalues? So for this we need to find the trace of the matrix, which is a 0, and the determinant of the matrix. Determinant of the matrix is -1. So from this we can write the secular equation, which is for a 2 by 2 matrix, lambda square minus trace lambda plus a determinant is equal to 0. This is the characteristic equation for a 2 by 2 matrix. So this is the lambda square, trace is a 0, and the determinant is -1 equal to 0. So which implies lambda is equal to plus or minus 1. So the eigenvalues of Pauli X matrix is a lambda equal to plus or minus 1. Not only X, Y, Z, everything is plus or minus 1. That means all these three Pauli matrices are having a same eigenvalues, lambda equal to plus or minus 1. Now let us find the eigenvectors now. Eigenvectors. Because for all those three matrices, trace is a 0 and a determinant is -1. That's why here you will get same eigenvalues. Okay, so first I am taking lambda is equal to plus 1. For this, I am going to find the eigenvector. So how to find the eigenvector? So the operator eigenvalue equation, a psi equal to lambda psi. Here our operator is 0, 1, 1, 0, and a psi unknown xy, and lambda we are finding for plus 1, so xy. So whenever you have a 2 by 2 matrix, so one equation is enough generally. If one equation is not enough, then go to the second equation. Now here row and a column, so we got y equal to x. If you multiply, here you will get y, first element, that y is equal to x. So this implies we can write the eigenvector xx, and we have to give the least integer, and we can give 1 1, so which gives 1 1, and the normalization constant is a 1 over root 2. So this is a x up. So generally this x up state is a 1 over root 2 and 1 1. So sometimes we will write this as a diagonal basis, that is a plus, get plus equal to 1 over root 2 or 1 1. This is the eigenvector corresponding to plus eigenvalue, plus 1 eigenvalue. So let us take a lambda equal to -1 now. So again the same technique. So here I am taking a Pauli X matrix, so 0, 1, 1, 0, and this is the psi xy. Now the eigenvalue is -1 xy. So here also one equation is enough. Take this row and a column. So you will get y equal to minus x. Here the first element is minus x, and here you will get y. So this gives y equal to minus x, means the psi equal to x minus x, because we got y equal to minus x. And this can be written as if you take x equal to 1, we'll get 1 minus 1. And the normalization constant is 1 by root 2. And this is represented by this diagonal basis minus 1 by root 2, 1, 1. Next, let us take Pauli y matrix. That means y equal to 0 minus iota, iota 0. So here eigenvalues are same. So that's why first I am taking lambda equal to plus 1. So now the eigenvector 0 minus iota, iota 0, and this is xy equal to 1 plus 1 eigenvalue xy. Now just multiply this row and column, we will get minus iota y equal to this is x. So which implies y is equal to iota x. Just always find y in terms of x, that's better. Now my eigenvector become x and iota x. because y is equal to iota x. Now take the least integer for this x, 1 over root 2, we can take 1 iota. That means I have taken x equal to 1. Right? And similarly, you please try for the next one. You will get for lambda equal to minus 1, you will get this 1 over root 2, 1 minus iota. I request you please try the second one yourself. And the next we have Z, Pauli Z matrix. So this is 1 0 0 minus 1. Here also same, trace is equal to 0 and a determinant equal to minus 1. That's why eigenvalues are lambda equal to plus or minus 1. Fine. So now we are going to find the eigenvectors corresponding to this Pauli Z matrix. So first let us take a lambda equal to plus 1. So we can take this operator 1 0 0 minus 1 operating on unknown xy equal to plus 1 xy. This is the eigenvalue equation. Just multiply this row and column, you will get x is equal to x. Of course, x equal to x. So here one equation is not sufficient. Then go to the next equation. Go to the take the help of the second equation also, because this won't decide. So x equal to x. Then if you take the second equation, row and column, if you multiply, you will get y equal to minus y. Now here is a point. Y equal to minus y. When it is possible? Only when y is equal to 0. That means x can be anything and y must be 0. So that's why I can take the least value 1. So this is represented by computational basis, that is a ket 0, which is a 1 0. X is 1, y is a 0. Still not understanding? Lambda equal to minus 1. For lambda equal to minus 1, 1 0 0 minus 1, and here is the unknown state, and minus 1 xy. Okay. So again take a first row and first column, I mean this row and column. So here you are getting this time x equal to minus x. X equal to minus x means obviously x is always a 0. And if you take this row and this column, we got minus y equal to minus y. That means we can take y equal to 1. So this is taken as another computational basis, ket 1, which is a 0 1. This is a Z up state corresponding to plus h cross by 2 eigenvalue or plus 1 eigenvalue, and this is a Z down state. But here we will represent in this notation ket 0 or ket 1 computational basis, right? So these are the eigenvalues and eigenvectors of Pauli matrices. And next he is asking one more thing, diagonal representation of the Pauli matrices. So this is very crucial. Diagonal representation. Diagonal representation. So let us suppose if a matrix is diagonalizable. So this is possible only when the matrix can be diagonalizable. Okay. So let A is a matrix. Let us say 2 by 2 or anything of order of n. Okay, is diagonalizable. Is diagonalizable. Then we can write this matrix A as this combination, linear combination, summation over I, lambda I, outer product, psi I, here outer product psi I. So what is this lambda I? This is the eigenvalue, and the corresponding eigenstate. Okay. So if the matrix is diagonalizable, we can write it as a linear combination of outer products of eigenvectors. Linear combination of outer product of its eigenvectors. And the coefficients are nothing but eigenvalues. Okay, so according to this, okay, so now if I take X, so this is a Pauli X matrix, which is a 0, 1, 1, 0. And we got two eigenvalues, plus 1 and a minus 1. So if this is the plus 1, and we got the eigenstate as a diagonal basis. And the next minus 1, we got minus. Sorry. So means this one. This is a 1 over root 2, 1, 1, which we have taken as a plus here. And this is minus. And similarly, if you take y, which is 0 minus iota, iota 0. And here we can write this as same eigenvalue plus 1. The corresponding eigenvector we can write like this also. It's not a problem. Or y up, you can write y up also. Minus 1, and let us take this notation clockwise or anti-clockwise, something like this. Or if you are having problem with this notation, take a y up here, y up, and this is a y down. So next one, if you take a z, 1, 0, 0, minus 1, and see here we got the eigenvalues plus 1, minus 1. Plus 1 eigenstate is a ket 0, minus 1 eigenstate is a ket 1. So that's why plus 1. The corresponding outer product 0, minus 1. We have to take the outer product of this one. So that is like this. So this is the diagonal representation of Pauli spin matrices. Pauli matrices. Of course, there's small difference between spin matrices and these things, right? Okay. If you have any doubt, so you please contact. Right. So this is the next question, and they are asking, show that this matrix is not diagonalizable. First of all, how can we say that this matrix is diagonalizable and this is not diagonalizable? Generally, if you get distinct eigenvalues, we can say, because the distinct eigenvalues will give you distinct eigenvectors, we can say it is a diagonalizable. But whenever we have degenerate eigenvalues, here is a problem. Degenerate eigenvalues may or may not give same eigenvectors. If a same eigenvector is given, there is no problem, it is not diagonalizable. Sometimes the degenerate eigenvalues also may give different eigenvectors. In that case, how can we say that this is a diagonalizable or not? For this, I will tell you one general method. So please listen carefully. Right. Now here the matrix given is 1, 0, 1, 1. So for example, if you find the eigenvalues for this, that means a trace is equal to 2, and a determinant, the determinant is equal to 1. Sorry, I think here it's not possible to, yeah. So here trace, this is also not visible. Okay, let's write here only. So now take this matrix, that is a 1, 0, 1, 1. Now I am taking this a trace is equal to 2, and a determinant is equal to 1. So if you take the secular equation, lambda square minus trace lambda plus a determinant equal to 0. This is a lambda square minus 2 lambda plus 1 equal to 0. We can write this as lambda minus 1 whole square. So that means here we got a lambda equal to 1 comma 1. So this is the degenerate, these are degenerate eigenvalues. Okay. Now, then how to check whether these same eigenvalues will give you the same eigenvectors or different eigenvectors? For this, we have to find one simple thing called multiplicity. So here we have two multiplicities. One is arithmetic multiplicity, we just will say it as a AM, and geometric multiplicity, geometric multiplicity. So let us say this as a simply GM. So what is this arithmetic multiplicity? Arithmetic multiplicity is simply just your Sickler equation. So what is your Sickler equation here? This is lambda minus 1 whole square equal to 0. So that means here lambda equal to 1 is the eigenvalue, but repeated how many times? 2 times. This power, just take this power. So arithmetic multiplicity in this case it is 2. Okay, so now what is this geometric multiplicity? Geometrical multiplicity is simply rank of A minus lambda I matrix. You have to find the rank of A minus lambda I matrix. First let me find this A minus lambda I. A minus lambda I matrix is nothing but just subtract 1 from here, 0 as it is, diagonal is 0, and here this 1 as it is. Now if you see carefully, this rank of this matrix, the rank of this matrix is equal to 1 because here we have a 1 non-zero element. So finally here what happened based on these two values, which is arithmetic multiplicity and geometric multiplicity, we got two cases. Sometimes this AM equal to GM if we can say that matrix is diagonalizable. If this arithmetic multiplicity is not equal to geometric multiplicity and this is not diagonalizable. So in this case our matrix 1 0 1 1 we got degenerate eigenvalues, but unfortunately arithmetic multiplicity is just a secular characteristic equation only. So here the power is 2, arithmetic multiplicity. Geometrical multiplicity means rank of A minus lambda I. So for whatever the eigenvalue you are finding, you just subtract that. That means A minus lambda I, and you will get one matrix. For that matrix, find the rank. That is called geometrical multiplicity. If both are same, it can be diagonalizable, and if it is not same, it is not diagonalizable. If any doubt, so please contact. So this is the next question. So they are asking these are the any two vectors, show that this one we have to show this Hermitian conjugate. Okay, so this we can do easily by using a direct notation. Okay, so already we know whenever we have this ket vector, its a complex conjugate is a bra vector, and the bra vector complex conjugate is a ket vector. By using this, for example, if you take this outer product, that is given outer product is W, here V state, and for this we are taking a Hermitian conjugate. Okay, so that means whenever you have taken this conjugate, ket will become bra and bra will become ket. That means this ket vector will go to this bra vector and this bra vector like this. So this is nothing but V here and W here. But let us find more generally. Okay, so more generally, if you want to find, first you please define that ket W is a linear combination of basis states lambda I Wi, where these are the bases and this is the linear combination. And similarly we also let us define this is the summation over J, lambda J and Vj. Okay, now I am taking this outer product, this one, this is W and V. So this is nothing but summation over I, lambda I, it is in the ket, so Wi, okay, so it is in the ket vector, and this is in the bra vector, summation over J, lambda J, Vj. Now earlier problems I already discussed. Whenever there is a constant in a ket vector, so this will be out as it is, and whenever there is a constant in a bra vector, it will be out with a complex conjugate. Constant you can write anywhere, no issue. So this implies this is the ket vector, that's why it will be out as it is, and after that we have wi. Let me write this also. And here this is the bra vector. This will be out with a complex conjugate by using this rule. And after that, whatever you have, just write down. Okay. Now this is outer product W and V. For this, we have to take the Hermitian conjugate, complex conjugate. So just take a complex conjugate. The summation over I as it is, this is a lambda I, it will become lambda I star, and this is the summation over j. This is already a conjugate is there, that's why the conjugate gone. And here as usual, ket vector will become bra vector and bra vector will become ket vector. That's it. Now again bring these constants inside. So here is a conjugate. So if it is a conjugate means it can go into this bra vector only. And here there is no conjugate, that's why we can write this into this ket vector. So this is just I am bringing this inside. Summation over j, summation over j lambda j Vj. And here we have a complex conjugate. That means we can write this inside the bra vector. Summation over I lambda I wi. Now again if you see this is nothing but our V, which is V state, and this is nothing but our W. That's it. So this complex conjugate is nothing but this one. Just so simple. The ket will become bra and bra will become ket. Like this. Okay. Right. So this is your next question. So they are asking this adjoint operator is antilinear. It's just expansion only, nothing else. So for example, if you take summation over I, AI, this is the operator, AI. This is the constant. So if you take the dagger, let us take the linear combination, that means expand it. So, or like this we can write. So this is the summation over I, this is AI star because we have to take a complex conjugate, and this is AI dagger. That's it. So if you expand this, this is nothing but A1 star, A1 cap plus A2 star, A2 cap plus A3 star, A3 cap, and so on. Sorry, and here you will get a dagger. That's it. But the next one is very important, and they are asking show that A dagger whole dagger equal to A. Okay, so we have to show this A dagger whole dagger equal to A. Okay, fine. So let us do this in two different ways. First way. Now I am considering this A operator operates on lambda. We got a lambda psi. This is just an eigenvalue equation. Okay. So for this, I am going to find a complex conjugate. Just find a complex conjugate. You know, ket will become bra, and the operator will get a dagger, right? So this ket vector will become bra vector, and this A will become A dagger. You should not write the operator beside this arrow mark. Always it should be beside this vertical line. And this complex conjugate is a lambda star, and a ket complex conjugate is a bra. Now again, one more time, just I am finding this complex conjugate or Hermitian conjugate. So again, one more time if you apply, again this bra will become ket, and this will get a whole dagger again. So that means A dagger, whole dagger, and this bra vector will become ket vector, and this lambda star whole star, and this ket will become a bra. So finally, if you observe carefully, A dagger whole dagger ket psi equal to, again we got lambda psi. So this is the first equation what we have assumed, and this is the second equation we got. The right hand sides are equal, so that's why we can say this left hand sides also must be equal. So we can conclude that this A dagger whole dagger equal to A. Let us do in another way also. Earlier we have discussed one concept called diagonalizable form, something Pauli matrices diagonalizable form. Yeah, here I think, yeah, this one. So if the matrix is diagonalizable, we can write it as a linear combination of outer products corresponding to the eigenstates. And the coefficients are nothing but the corresponding eigenvalues. I'm using this. So now let us suppose our matrix, our operator A, the corresponding matrix, because every operator is represented by square matrix. The matrix, corresponding matrix is diagonalizable. Okay, then if it is diagonalizable, we can write this A operator as the linear combination summation over I lambda I outer products psi I psi I. Remember, this lambda I is nothing but eigenvalues of A, and these are the eigenstates. So now let us apply dagger for this. That means a Hermitian conjugate. If I apply dagger, this is a summation over I. Lambda will get a star, and ket will become bra, and bra will become ket. Of course, so both are same. That's why no change. And one more time apply a dagger. So this is the summation over I, lambda I star whole star, and again this ket goes to bra, and bra become this ket vector. So there will be no change, got the same thing. So as usual, this becomes summation over I lambda I, so here conjugate, whole conjugate, and this is psi I psi I. This is A dagger whole dagger. Now if you observe this first equation and the second equation, the left hands are same, and we can say that the right hands are same. A dagger whole dagger equal to A. So I have done in two ways. Whatever you feel easy, you just follow that. So right, let us go to the next question. So here they are asking about projection operator, so which satisfies p square equal to p. That means idempotent. So they are asking to show that projection operator is idempotent. So first let us talk about this projection operator. So projection operator is nothing but outer product. So this is the outer product only, which is given by outer product. Inner product is a scalar which gives the probability amplitude. Inner product will give you probability amplitude, and outer product of any two state vectors, if you take it acts like an operator. Okay, so here projection operator means, let us define this p psi, this is equal to psi psi. It should be same. That is the difference between general operator and projection operator. So this bra and ket, these two must be same. I hope you understand. So this is your projection operator. Now let us find its properties. Now I am applying the Hermitian conjugate p psi dagger. I told you earlier. So it's just psi psi outer product, apply whole dagger. So this ket vector will become bra, and bra vector will become ket. Of course, again you got the same thing. So we can say that p psi dagger equal to p psi, which is a self-adjoint or Hermitian. Hermitian operator, or we can call it as a self-adjoint. And the next one, so here they're asking the another one, that is p square. So here I have taken p psi, which is the outer product psi psi. Now I'm taking a p psi whole square. You just multiply 2 times. This is psi, and again one more time. And if you see carefully here, we got the inner product, that is the inner product psi psi, which is equal to 1. So again we got the outer product psi, so which is equal to again p psi, so which is idempotent. So p square, I mean p psi square is equal to this p psi. Next here they are asking, show that a normal matrix is a Hermitian if and only if it has a real eigenvalues. That means here they are asking to show that a Hermitian operator is having eigenvalues real. Okay, so let us do this in 2 ways again. Let us take the first one. So now I am assuming let A is a Hermitian operator. A Hermitian operator. Okay. So what is the meaning of this? A is a Hermitian operator. We can write this as A dagger equal to A. This is the self-adjoint. Self-adjoint. Okay, fine. Now I am assuming an eigenvalue equation corresponding to this A psi equal to lambda psi. Okay, right. Now just multiplying this, that means let it be equation 1. I'm just multiplying on both sides with the bra psi, that is bra psi A. I will write here maybe. So multiply, later if you verify, multiply with bra psi on both sides. This is the bra psi A ket psi equal to, so lambda constant and psi psi. So this is equal to 1. So we got psi A psi equal to lambda. Let it be equation 1. Next, I'm taking this complex conjugate here. So whatever first I have assumed, just I'm taking the complex conjugate. Then this bra vector will become ket vector, and this A will get a Hermitian conjugate, and a lambda will become lambda star, and again ket will become a bra vector. Now this is my second equation. So here I am going to multiply with this time ket vector of psi. So if you multiply bra psi A dagger psi equal to lambda star psi, and this is equal to 1, and we left with the psi A dagger psi equal to lambda star. Now carefully observe this 1 and 2 equations. So here it is, this is the matrix element of course, and of course this is also, we call it as matrix element. Okay, so anyhow, here A and A dagger, but already we have taken A is a Hermitian operator, so that's why A dagger is equal to A. So the left hand sides are equal. So yeah, well, left hand sides are equal, then we can say lambda star must be equal to lambda. Why? Since A is a Hermitian and A dagger is equal to A. Okay, this is one way of doing by taking the eigenvalue equation. Now let us take a diagonalizable form, second way. This is the first way. So whatever you feel easy, you just take that. Okay, so a second way. Now let that operator A is diagonalizable. So this condition must be satisfied, otherwise we can't do this. Let it be diagonalizable. Whenever a matrix is diagonalizable, so that we can write it as a summation over I, lambda I outer products. That is a linear combination of outer products or corresponding to eigenvectors, and the coefficients are nothing but eigenvalues. Okay, so now what I'm doing is I'm just applying a dagger for this. This is a summation over I, and here we have lambda I star, and again the same technique. The ket become bra and bra become ket, and fortunately both are same, no change. That's it. Now if you just compare, this is equation 1 and this is equation 2. Just compare, no need to do any mathematics here. So these two are equal, since A is a Hermitian, that means A dagger equal to A. So we can say lambda I star must be equal to lambda. That means what? Real. So eigenvalues of a Hermitian matrix are always real. Eigenvalues of Hermitian operator. Hermitian operator are real. Now you may get one doubt. If it is anti-Hermitian, what about the eigenvalues? Anti-Hermitian eigenvalues are either 0 or pure imaginary. Anti-Hermitian eigenvalues are either 0 or pure imaginary, but Hermitian operator eigenvalues are always real. Right. So let us go to the next question. So here they are asking, show that the eigenvalues of unitary matrix have unit modulus. That means whose modulus of, modulus of the eigenvalue should be equal to 1. And it can be written in the form of e raised to I theta. Okay, so now let us do this easily, don't make it complicated. So I'm assuming U is a unitary, U cap is a unitary, here matrix, that's why simply you can take U. U is a unitary matrix, So what is the meaning of this unitary matrix? This means U dagger into U equal to U into U dagger equal to identity. Okay, let us take eigenvalue equation. So I'm taking this eigenvalue equation corresponding to this unitary operator, which is U operates on psi, we got lambda psi. This is the eigenvalue equation. Let it be equation 1, and just I am taking the complex conjugate of this. Just to take the complex conjugate, which is a bra psi, and this U get a Hermitian conjugate, and this is a lambda star, and this is a bra psi. Let it be equation 2. Just multiply these two. Generally, whenever you are multiplying, the first we have to write this bra vector. Just multiply 1 and 2. Multiply this 1 and 2. So here if you multiply psi, U dagger, U and psi equal to this lambda star into lambda, and we can write this as a mod lambda square. So I hope you got this, otherwise I will write one more step. Lambda star into lambda, and this is a psi. This is equal to 1, okay, and I hope you know from the property of this unitary matrix, this is I, and finally we got psi I psi equal to mod lambda square. Okay, now just operate that. Whenever this identity operator operate on this psi, you will get the same. That's why one more time let me write here. We got lambda square. So this implies this is nothing but psi, which is equal to lambda square. Of course, this is also 1. So lambda square, mod lambda square is equal to 1. and we can say this modulus lambda is also equal to 1. That's it. So, and the next one, what he's asking, it should be written in the form of e raised to I theta. If let us suppose lambda is equal to e raised to I theta, and if I take the modulus, this is e raised to I theta, which is nothing but cos theta plus iota sine theta, and this is a modulus cos theta plus iota sine theta, and this is nothing but under root cos square theta plus sine square theta, because the complex number z is equal to a plus iota b, then mod z is under root a square plus b square, which is equal to 1. So the eigenvalues of unitary matrix are unit modulus. So it means if you find its modulus, always it is equal to 1. Or we can write the eigenvalues in the form of lambda equal to e raised to I theta. This is very crucial for our coming quantum circuit lectures. So here, this is our next question. Show that Pauli matrices are Hermitian and unitary. So, okay, let us check. Pauli matrix, Hermitian and unitary. Hermitian means self-adjoint, whose dagger is equal to same, and unitary, the product of dagger and that matrix should be equal to identity matrix. Okay, so let us start. So this is our Pauli spin matrix X 0 1 1 0. Now I'm taking the corresponding dagger, means you have to convert rows to columns or columns to rows. Don't do the both the things, okay? Either rows to columns or columns to rows. And you have to take the corresponding complex conjugate. But unfortunately here these are real, that's why we won't get any change here. So once you got this, we can find the product, of course, here both are same, x equal to x dagger, so we can say it is a Hermitian operator. And the next I'm going to take the product, that is x into x dagger, so which is a 0 1 1 0, and this is a 0 1 1 0. So of course Pauli spin matrices satisfies this property whose square is equal to I, identity, that is called involutory property. So if you make this product, this is equal to I. And second one, so it's a Hermitian and here it is unitary. And let us take Y. So Y, this is the matrix, so 0 minus iota, iota 0. And I'm finding the corresponding Hermitian conjugate or dagger. So you have to take this row and write it as a column, but with a Hermitian conjugate or complex conjugate, that is a 0 iota. Take this row and write it as a column with the Hermitian conjugate, that is minus iota 0, complex conjugate, sorry. And here both are same, that's why we can say Hermitian, y equal to y dagger, which is Hermitian. And after that, just take the product y into y dagger. So this is just 0 minus iota, iota 0. And this is also same again, 0 minus iota, iota 0. So same involutory property, or if you multiply these two matrices, you will get I, that is a 1 0, a 0 1. The third one you please try yourself, that is third one also z equal to z dagger and z into z dagger equal to I. So the Pauli spin matrices are both Hermitian as well as unitary matrices. Let us do in another way. So earlier we have discussed this diagonal form. What is that? Or outer product form. Let us take outer product form. Okay, both are same only, but take outer product form. So outer product form means earlier examples I explained how to write the outer product form. Whenever an operator is there, so it can be written as a simply like this. Psi initial, sorry, this is a linear combination of summation over I, psi initial and psi final. You have to take a uh, I mean input and output. This is I'm sorry, 1 minute. Okay, I'm sorry. So here I'm using this second method also. So earlier, if you observe carefully, I explained one more thing, one more representation, outer product form. What I explained, this is the summation, initial state, and this is the final state. Or we can say like this is the input and this is the output. You have to write the outer product form. In the ket vector, you have to take the input, means the input corresponding to this operator, and whatever the output you are getting, write in the bra vector. Already I have explained earlier. So first let us take a x operator. So if you give the input as a 0, you will get the output 1, plus if you get 1 as the input, you will get a 0. So this is the outer product form of x. Okay, and if I take a x dagger to this, which is bra will become ket will become bra, and here also the same. So this will become 1, a 0, and this is a 0, 1. Both are same. So this is x dagger equal to x. Now if I take the product x into x dagger, just to take the product. This is outer product 0, 1 plus 1, 0, and product with 1, 0 plus 0, 1. Now whenever you are multiplying, so here it is outer product 1, 0. This will be multiplied with this. Then 1, 1 will become 1, and you remain with here 0 and here 0. That is 0, 0. Next, this one with here, 1 with a 0 inner product. This will give you 0, leave it. And again, next this term. This 0 will be multiplied with 1, you'll get 0, leave it. And the second term with the second term will give you non-zero, because here 0, 0 will give you 1 plus the remaining 1 and 1. This is nothing but identity operator. In the earlier problems I have already explained, please check that. So finally we can say that x into x dagger is equal to I. I will find that y also, and after that you please try that z yourself. Now here I am taking y. So what is this y operation? If you remember, y operates on 0, you will get iota 1. Y operates on 1, you will get minus iota 0. Right. So y input is a 0, output iota 1, plus input is 1, output is iota 0. Sorry, minus iota 0. Once again, 0 input, iota 1 output, 1 input, minus iota 0 output. This can be written as, this is iota is in the bra vector, it will come out with minus iota 0, 1. And here this is a minus iota in the bra vector as usual. This is a plus iota, here 1 and a 0 as it is. So this is the our outer product form of y. Now I am finding this y dagger. This minus iota become iota. So this ket vector will become bra vector, and bra vector will become ket vector. So as usual, so this will become 1 and a 0. This iota will become minus iota. The ket vector will become bra vector will become ket vector. That's it. And if you see, both are same. So here y dagger equal to y, which is a Hermitian. If you multiply both, that is a y into y dagger. So this is a minus iota, outer product, 1, plus iota, outer product, and it is multiplied with y dagger. This is iota 1, 0, and minus iota, outer product 0, 1. If you just multiply the same technique, first will be multiplied with the first and the second will be multiplied with the second term, because other cross terms will be 0. So here iota and minus iota, which is equal to 1, iota minus iota, iota 1. So this 1 and 1 inner product is equal to 1. You remain with a 0, 0. Similarly, this minus iota into plus iota, again plus 1, and here you left with 1. So which is equal to I. Now I request you, please do the third one yourself. If you have any doubt, please contact. That means take a Z. So Z, you know, input is 0, ket 0, computational basis. Output is also 0. Z operates on 1, we will get a minus 1. So by using that, I request you please try this method, very useful for our other discussions. Right. So here this is our next question, and here they have given the matrix representations in two different bases. In the basis Vi, that matrix element represented or matrix is given by A prime, and this is the corresponding matrix element in this basis. And here this is the matrix element representation in this basis. So now what they are asking is a relation between that A prime and A double prime. So we have to find the relation between these two matrix elements. Remember, whenever there is a concept of a change of basis, always use the completeness rule. So I told you earlier, the completeness rule. So completeness rule, this is nothing but identity operator, the summation over I, this outer products, or projection operator. So this should be equal to I, identity operator. Okay, now let us start with this. So we have to find the relation between these two. So first I'm taking this A prime in the basis of Vi, and this is the A double prime, this is in the basis of W. Okay, so we have to find the relation between this. Now let me take this matrix element A prime ith row jth column equal to this one. So Vi A, matrix is A only here, A, and this is Vj, because we are representing the same operator in two different bases. Okay, this one. Now we would like to transform into this basis. That's why you better to write this as Vi, write one identity here, A operator, and one more identity, okay, so into Vj. Now I am going to write this I as summation. I and j already taken dummy indices. I just take another index k, so which is another basis. This is the outer product. So next this I, please take another index, no problem, L, and again WL. That's it. So just take it and substitute. So this is I'm writing this as summation outs, summation, this summation is out, summation over k, and here it is Vi, and here we got the inner product, this one I have to write here, which is Wk, and again this is summation over L, I'm writing here, okay. So this is again we have we have A here, and after that this one. So please check if any doubt. And the last one is as usual. Now carefully observe. See, this is some scalar product between these two, and here we have this operation, and again something. If you observe carefully, this is related to this one. Okay, so I hope you understand what I'm saying. This is the operator A representation in W basis. Please check W basis. Don't bother about this dummy indices. So this is nothing but A double prime KL, because here we have K and L, no issue. So finally we have A prime Ij equal to, so we got a summation over K and a summation over L, and here we have this Vi Wk, and after that we have A double prime, so this is the KL matrix element, and after that whatever you have, that is remains as it is. Here is no space, let me so this is here, this one I'm writing here, so WL and Vj. So finally we can write this as A prime Ij equal to summation KL, and this is Vi Wk A double prime KL, and this is WL and Vj. That's it. So this is the transformation of this matrix elements, of course, right? This is the transformation from one basis to another basis. So if you have any doubt, so please contact. Okay, so thank you. So please go through these solutions, and if you have any doubts, so please contact. Okay, thank you.